Welcome to Spring LIB.
This exercise, we're going to be talking about circular motion and elastic force. So before actually solving the problem, I'm going to give a brief review. First, you have to remember that the acceleration of an object that's undergoing circular motion is equal to the speed of the object squared divided by the radius of the trajectory. Also, we need to remember that the elastic force F has a magnitude that's equal to the stiffness of the spring, K, times the displacement of the string from its equilibrium position, delta x. And we have to remember also that the force points in the opposite direction as the displacement of the spring. And this information is all we need in order to solve our exercise. So what we have is a spring that's connected to a collar. The spring has a stiffness of 200 newtons per meter, and the collar has a mass of 0.75 kilograms. The spring is unstretched when S, here in the figure, is equal to 0, and we want the string to be stretched at distance S of 100 millimeter, which is the same as 0.1 meters. And we want this to happen using a certain speed that's given to the whole system that makes the system rotate. And our goal is to find what should be the speed of the collar in this rotation so that S is equal to 0.1 meters. Okay, so all we need to do is to draw a force diagram on the collar. So we have the elastic force that points in this direction. It's the same direction as the spring. Let me do it like this. Okay, again, this is the elastic force. And also we have the normal force and the gravitational force, mg. One of the tasks that the exercise gives us is to find the normal force. Notice that the color is not moving in the vertical direction, so necessarily the normal balances the gravitational force. So the normal is equal to mg. Now notice that m is 0.75 kilograms and g is 9.8 meters per second squared. So N is equal to 7.36 newtons. This is the normal force. And we must also find V. Now notice that the only force in the horizontal direction is the elastic force F, and this is equal to the mass, according to Newton's second law, times the acceleration. And as I said, the acceleration is V squared over R, because the collar is moving in a circular motion. Now F is K times delta x, which is just S, which is 100 millimeters, since it's the difference between the stretched position, which is 100 millimeters, and the unstretched position, which is 0 millimeters. And this is equal to M times V squared over R. And we want to find V. So V is equal to the square root of RKS divided by M. R is the radius, which is 0.1 meters. K is 200 newtons per meter. And S, and I'm sorry, S and K, S and R are actually the same thing, of course, because the radius, notice in the figure that the radius of the orbit is equal to s, since the center of trajectory passes through s equals 0, so r is equal to s. So actually what we have is k times s squared. So we have another s here, divided by m, which is 0.75 kilograms. So v is equal to 1.63 meters per second, which is the final answer to our exercise.